Assalamualaikum and very good day to all of you. Okay, so we're going to enter a new chapter, which is chapter 6. In chapter 6, okay, we will learn about friction and minor losses. Okay, so this is the learning outcome that we expect you to gain after completing chapter 6. Okay, so since that chapter 6 is quite long, so I have divided into two main parts. Okay, so if you look at here, the first part is more about theoretical, in which that we will learn how can we determine the friction factor, or we call it equivalent friction factor, in two conditions, which is laminar and turbulent flow. Okay, so if it's laminar, we use Darcy's equation, and if it's turbulent, there's a method, we call it as using Moody's diagram. Okay, and in the next video, which is I'm going to cover part 2. Okay, so part 2 is more on the application of the friction and losses in a flow system, okay, in which that we're gonna learn how can we determine the friction energy losses in a few in many conditions. Okay, so for example, like if it's the flow is occur in non-circular section, and if it is occur in a sudden or gradual enlargement or contraction, and other parts which is involved in a piping system or flow system. Well, this is the outline which we're going to cover in this chapter. The first part is we will cover about the Darcy's equation, okay? And then we will proceed with the calculation or determine how can you determine the friction and minor losses in two different cases, which is in laminar and turbulent flows. And we will also cover how can we determine the friction loss in non-circular section. Okay, so basically number 2 is we encounter the case in which that the flow happen in a pipe or in circular pipe. Okay, and this one which is when the flow happen in non-circular, which is the geometrical of the flow is not in a shape of circular. Okay, so that's why it calls a non-circular cross section. What is Darcy's equation? How can it be used in a calculation or determine the friction loss? Well, in order to determine the energy loss due to the friction, this is the equation that we're going to use. Okay. So from this equation, the H here is stand for energy loss, which is HL. Okay. If you still remember in a previous chapter in which that we will learn about the equation of energy, okay, we did have this term in the equation, okay, energy equation, which is referred to energy loss due to the friction. So in this chapter, we're going to concentrate on how can we calculate these parameters. Okay, so the L here is actually length of pipe, okay, length of flow stream, and D is stand for diameter. V is just average flows of average velocity of flows, and F is basically the friction factor. Okay, so this equation, okay, we can only be used, okay, in the case of long straight section of round pipe. Okay, so that means it's just for the flow which is occur in a pipe. Okay, and for the fluid in the category of laminar and turbulent. Okay, and F here, okay, it will change depend whether it is laminar or turbulent. Okay, so in the next part, I will explain how can we determine this F in order to calculate the energy loss in two conditions, which is laminar and turbulent. All right. Okay, let's proceed with the first type of flow. Okay, how can we calculate the friction and minor losses in laminar flows? So when a laminar flow exists, okay, there's a shear stress, okay, is created between the layer of fluid due to the viscosity of fluid. Okay, so just imagine that inside a pipe, Okay, so the fluid will fill up the space inside the flow. Okay, so there will be a shear stress between the fluid inside the pipe here. Okay, that's why there's a shear stress that actually creates the losses inside the pipe. Okay, so in order to overcome the frictional force produced by the shear stress, okay, the energy loss from the fluid. Okay, so usually HAIGEN-POSSEILI equation was developed to relate the energy loss. Okay, so before this, I already introduced you the Darcy equation to calculate the HL. Okay, and then now we're gonna relate it with the HAIGEN-POSSEILI equation. Okay, so this is the HAIGEN-POSSEILI equation. Okay, so the energy losses in laminar does not rely on the condition of. Okay, so now I will show you how can we relate between the Darcy equation and HAIGEN-POSSEILI equation in order to calculate the energy loss or HL occur in laminar flow. Okay, so if you look at here, on the left side we have Darcy's equation and on the right side we have HAIGEN-POSSEILI equation. So both of the equation is we want to get the HL. Okay, so this is HL from HAIGEN and this is HL, how to calculate HL from Darcy's equation. So we equate, okay, between these two equations, okay, and then finally we will get this term. Okay, and we know that since that rho equals to y over g, so that F here, okay, is actually equal to this term. And since that Reynolds number is actually rho Vd divided by rho Vd divided by mu, which is the viscosity. And lastly, we can simplify this equation into this equation, which is F, the friction factor, will be equals to 64 divided by Reynolds number. So this is actually how can you calculate the F, the friction factor, for the laminar flow. Okay, let's try to do this example. Okay, so for example here, the equation says that, so you need to determine the energy losses, which is HL, if glycerin, okay, the fluid is glycerin flows at 25 degrees C, 30 meters. So this one is actually length of the pipe through a 150 millimeter, which is diameter of the pipe, with the average velocity 4 meters per second. So this is actually V. So knowing that the specific gravity for glycerin at 25 degrees C is 1.258. So this is specific gravity. Okay, or actually the gravity of glycerin divided by gravity, the density of glycerin divided by density of water. Okay, which is equals to 1.258. And lastly, this is actually the viscosity of the glycerin. Okay, so you need to determine what is the HL. Okay, so how can we solve it? Okay, remember we have the term of F equals to 64 divided by Reynolds number, in which that is just to calculate the F. And how about the HL? Okay, so let's see how can we solve this problem. Okay, so as usual, what you need to do is you need to list down all the info which is given from the question and plan the formula that you can use to solve the problem. Okay, so we certainly know that this is the equation that we can use to calculate the HL, which is F times with the L over D times with V to the power of 2 divided by 2G. And then we know that the F actually can determine from this equation. This is how to calculate the F for the condition of laminar flow. Okay, so here is the information which is listed down from the equation. So for example, the length is given 30 meter. Okay, and the diameter of the pipe is also given 0.15, and velocity is given, and density, as I said, density is actually, the specific gravity is actually the ratio between density of glycerin divided by density of water. Okay, and lastly, the dynamic viscosity. So this is the viscosity of the glycerin. Okay, so we certainly know that the density of glycerin is not given, but you can get it from information here. Okay, and gravity acceleration, or G, we know that is 9.81, and density of water, certainly we know that it is 1000. Why we need this? Because that we're going to substitute into here. Okay, so that we will get what is the density of glycerin here. Okay. Okay, so we already have the info, we already have the formula plan. So what's next that you should do is substitute into the formula. Okay, so here I repeat again, this is the formula that you need to use. Okay, so all the information, all the parameters inside here, you just need to substitute. Okay, so first of all, definitely you need to get this F value first before you can get the HL. So in order to calculate F, you need the Reynolds number. Okay, so let's check it out here. Okay, so you already have the density. So Reynolds number, of course, you can calculate it because the Reynolds number is actually rho V D divided by mu. Okay, so rho, you already have the information of rho here. Okay, so viscosity, we already have the viscosity given in the equation. Okay, viscosity, we already have it, and diameter also we have it, and which is given in equation, and then the viscosity also given in the equation. So substitute it and you will get your F. So basically this is your Reynolds number. Okay, once you get your Reynolds number, you substitute into equation F here. Okay, and then you will get your F is actually equals to 0.081. Okay, so once you are done with the F, you just substitute into this formula. Okay, so F is 0.81. Okay, and then the rest of the value, you just substitute the value, and finally you will get that the HL is actually 13.28 meter. Easy peasy. That's it. Okay, since we are done with the laminar flow, now we proceed with the next part, which is turbulent flows. How can you calculate the HL, which is occur in turbulent flow system? Okay, so if you remember that in chapter 5, okay, the flow which is occur in turbulent flow, it is a very chaotic situation and it keeps on wearing. Okay, so that's why it is quite tricky to determine the effect of energy loss in a turbulent flow system. Okay, so therefore the F calculation cannot be used by the simple calculation. We have to use the experimental data, or we need a diagram for it. Okay, so basically, in order to calculate the friction loss due to the occur in a turbulent flow, F very relies on Reynolds number, and it is related as well to the roughness of the pipe. Okay, so this is condition inside a pipe. Okay, so for example, if you can see the effect here inside a pipe, okay, there's a surface of the pipe which is it might contributes or it might influence the friction loss occur inside a pipe. Okay, so that's why we see here the surface roughness is very important parameters. Okay, so dimensionless number F is actually depend on Reynolds number and relative roughness of the pipe. Okay, so what is the relative roughness of the pipe? Okay, so this is the formula to calculate the relative roughness. Is actually the ratio between D, the diameter of the pipe, okay, divided by average wall roughness. Okay, this is the roughness. Okay, so for example, if the surface is quite smooth, so the roughness should be lower. If the surface is very rough surface, so the roughness will be higher. Okay, so this is the formula to calculate the relative roughness parameter. Okay, and here we have the list of different materials, okay, with its value of the surface roughness. If you can see here, for glass, it didn't have any surface roughness because it is categorized as it has very smooth surface. In fact, plastic does have the surface roughness, okay, but it's quite small. See, it's -7. Okay, so we need to include this parameter in order to calculate the relative roughness of the certain surface of the pipe. Okay, so basically this is the Moody chart that we're going to use to get the friction factor, okay, for the flow in turbulent region. Okay, so basically on the x-axis you have the Reynolds number, and you also need this value, which is the relative roughness. Okay, this one is very careful. It's very important. You have to look at it carefully whether the information provided here, whether E over D or D over E. Sometimes they do provide you Moody's chart with D over E or E over D. Okay, so for example, this one is E over D. Okay. Okay, let's try. Okay, so for example, if the Reynolds number is 2 times 10 to the power of 6, which is here. Okay, and then the relative roughness E over D equals to let's say is 0.0004. Okay, so this is the relative roughness for 0.04. This is the line here. Okay, so it goes along here. So since that your Reynolds number is here, so this is basically the line for Reynolds number 2 times 10 to the power of 6. So this is the cross section. Okay, so you just need to bring it towards the y-axis where you can get the F. So basically here is F equals to 0.016. That's it. Okay, so here is another form of Moody chart. Okay, what is the difference between this one and the previous one is, if you look at here, is actually D over E. Okay, the one that I show you in the previous slide is actually E over D. So it's more or less the same. Okay, you just need the Reynolds number on the x-axis, and you need to know what is the ratio between D to E, the relative roughness. And then when you get the cross section, and then you just go straight to the y-axis to get the value of Ft. Okay. Okay. So since that Moody's chart is very important, okay, you're gonna use it later on in part 2 as well. So you need to be expert how to use the Moody chart. Okay, so just test yourself whether you will be able to determine the F or not. F based on the Reynolds number and the relative roughness. Okay, so for example, the first one, okay, can you get the answer? If the Reynolds number is 6.7 times 10 to the power of 3 and the relative roughness is 150, you will get that F equals to 0.0430. And if the Reynolds number is 1.6 times 10 to the power of 4, you will, and the D over E is 2000, you will get the F equals to 0.0284 and so on. Okay, I hope that you can try it by yourself. So this is the answer. Number 3 is 0.0171. And okay, let's try this one. Okay, the first one, if the Reynolds number is 6.7 times 10 to the power of 3 and the relative roughness is D over E equals to 150, what is your F? Okay, so you have to use the Moody's chart. Okay, since that we know that the Reynolds number is 6.7, which is on the x-axis. So here, okay. And then we determine the D over E, which is given 150. So here is 150. Okay. So this is the line for 150. So you just need to get where is the cross section between D to E and Reynolds number. So here is the cross section. Okay, so which is F equals to 0.0430. That's it. Okay, let's try this second example in order to calculate the friction factor, the F, in a case of water which is flow at 70 dc. And this is the velocity, which is 9.14 meter per second in ductile iron pipe. So this is the categories of the pipe. Okay, you need this information that because that you will want to get what is the roughness for this category of pipe. Okay, and having an inside diameter of 25 millimeter. So this is the D in. Okay, it is known that the kinematic viscosity of the fluid is given here. Okay, so how can you get the F? Okay, so let's check it out. How can you solve this problem? Okay, so let's take a look at how can you solve this problem for the energy loss in turbulent flow case. Okay, but we're not gonna calculate up to HL. We just want to get the FT. Okay, so you just need to list down all the info provided from the question and list down or plan the formula. Okay, so this is the information you have from the question. You need to get the surface roughness. It is not given in the question, but the question tell you it is actually category of ductile iron pipe. Okay, so you can get the value from table 8.2. And the diameter is given, which is 0.025. Velocity also given, which is 9.14. And kinematic viscosity also given, which is 4.11 times 10 to the power of minus 7. Okay, so we certainly know that, okay, we need this Moody's chart. Why? Because we want to get the FT here, the F, friction factor, okay? So to calculate the Reynolds number, we have this formula. Okay, note that the Reynolds number, you can also use this, the first one, which is rho V D divided by mu. Okay, this one is actually the dynamic viscosity. If it's kinematic viscosity, we can use this one because the kinematic viscosity is actually the ratio between rho divided by mu. Okay, so that's it. Let's see how can you substitute into the equation. And don't forget that you need as well info about the relative roughness. Okay, because that you can get this information from the table 8.2. So you need to substitute it. And you do have the diameter. So you already have the info on the other axis. Okay. So you have the x-axis and the other axis as well. And you can get what is your friction factor. Okay, so you can just substitute into the formula. Okay, so this is actually the output from the calculation. Okay, well, it may be quite confusing because from the question, the given value of viscosity is actually the kinematic viscosity. Okay, but here is actually dynamic viscosity. So this one is actually dynamic viscosity. Okay, don't be confused. It's actually like this. Reynolds number equals to V D K times with rho and divide by mu, which is equals to V D divide by this kinematic viscosity. So this is actually kinematic viscosity. Don't worry, the symbol is quite confusing. Okay, so this is actually V, this is actually kinematic viscosity. Okay, I don't want to confuse it, I just make it capital letter like this. So basically, okay, 1 over kinematic viscosity is actually equals to rho divided by dynamic viscosity. Okay, so therefore in this case you can just calculate the Reynolds number, okay, by multiply between V times D divided by kinematic viscosity. Okay, so here is your Reynolds number, and you already have, you can you can find the surface roughness from table 8.2, which is 2.4 times 10 to the power of minus 4 in the category of ductile iron pipe surface. And once you have the value, you can divide between diameter divided by surface roughness. So this is the surface roughness, the value of E. Okay, and D is given, and you get this value. And this is the value on the other axis. Okay, you need this info, and you already have the info for Reynolds number. Okay, so you just substitute it into here, which is 5.6 times 10 to the power of minus 5, which is somewhere here. Okay, and you get what is your D over E, which is about 100 something. So maybe at the top here. And finally, you will get the F. Okay, so F is actually 0.038. So as expected lah. Okay, F actually 0.038. So somewhere around here. Okay, that's it. You already get the F value. Okay, so previously, okay, our calculation is by assuming that the pipe is actually in a circular form or in a shape of pipe, normal pipe. Okay, so what if the floors exist in a non-circular cross section? Okay, or it didn't flow in a circular pipe. Okay. Okay, so Darcy's equation for friction loss can be used for non-circular cross-section if geometry is represented by hydraulic radius instead of pipe diameter. Okay, remember that in order to calculate Reynolds number, we need D, the diameter. In order to calculate the relative surface roughness, we also need D. Okay, and in order to calculate the HL, we also need D. Okay, but since that the shape is no longer in a circular shape, so we don't have this D value. So we don't have. So how can we calculate the Reynolds number? So because the Reynolds number, we need D. And same goes to the relative roughness, in which that we need D over surface roughness. We don't have this D. Okay, and same goes to the Darcy equation, in which that we do need the D inside the parameter. Okay, so still we cannot solve it. Okay, but there's a method to solve it, in which that we will use hydraulic radius. Okay, hydraulic radius. Okay, so let's take a look at here. Okay, so this D actually we represent by this term. We multiply 4 multiply with this R. R here is not normal radius, it's actually hydraulic radius. How can we determine the hydraulic radius? Okay, later on I will show to you. I just want to list down how this non-circular section affect our equation. Okay, so therefore we will substitute into 4R. Between D we will substitute with 4R. Okay, same goes to relative roughness. We will substitute this D with the 4R. Okay, and same goes to the Darcy equation to calculate the HL. Okay, we replace D with 4R. Okay. Okay, so how to calculate the Reynolds number? Okay, if there is no radius for non-circular section, so this is what I'm talking just now. Okay, if the shape is non-circular, so we don't have the D. For example, like the flow flows inside it, so we don't have the D. Okay, that's why we introduced the hydraulic radius, R. Okay, so the hydraulic radius is actually can be determined by the ratio between area divided by wetted perimeter. So all of this actually it depends on the geometric shape of the flow section. Okay, I'm going to show you later. There are a few types of shape, okay, which can we use, okay, in a fluid flow system in a case of non-circular section. Okay, so this is the formula to calculate the hydraulic radius, which is area divided by wetted perimeter. Okay, and this one is actually the example, the 4 example of non-circular flow section. Okay, don't be confused with the diagram. So if you see that the shaded area is actually where the flow occur. Okay, so the liquid flow inside it, and here is there's another shape of pipe inside it. Okay, so that's why area here is actually the area of bigger diameter minus with area with the smaller diameter. Okay, and the wetted perimeter as given here. Okay, not parameter, perimeter. Okay, so the second shape is just a rectangular shape. Okay, so the area is given here, and the wetted perimeter is also given here, which is 4 times S. Okay, and this shape area is B times H, and the wetted perimeter is like this. And the other one, which is there's a circular inside the rectangular shape. Okay, so this is the way to calculate the area and the wetted perimeter. So what is wetted perimeter? Wetted perimeter is basically defined as a sum of length of the boundaries of the section actually in contact with the liquid or fluid. Okay, therefore the Reynolds number you can calculate it by using this formula, which is rho V. This one is actually the other terms to calculate to define V. V here is actually velocity. And then times with 4R. Remember that if it's circular, we use D. But now if it's not circular, we use 4R. 4 times with the R. R is actually hydraulic radius. The hydraulic radius, we use this term to calculate the hydraulic radius divided by viscosity. Okay, that's it. So now we come to the end of part 1 for chapter 6. Okay, so I hope that you continue to watch the part 2 video for chapter 6. Thank you very much.